Situated 100 light-years away, the star HD110067 boasts a planetary system characterised by an unprecedented level of perfection. Scientists believe its formation was the polar opposite to the tumultuous beginnings that marks the creation of our own solar system, where a unique arrangement of 6 planets with orbits impeccably synchronised is offering scientists a near-perfect laboratory in which to observe a planetary system preserved as it existed billions of years ago. Welcome then, and join me, the Cosmic Skipper, as we look at what we know so far about the planetary system around HD 110067 and why it could prove so important in developing our understanding for the evolution of planetary systems. Marked by violent collisions between planetesimals and protoplanets, our solar system's formation was chaotic, giving us the diverse array of planets we have today. The 4 terrestrial worlds of Mercury, Venus, Earth and Mars reside within the inner solar system, whilst 2 gravitationally dominant gas giants in Jupiter and Saturn have shaped and affected the orbits of planets in the solar system, and still do to this day. Outside these 2 behemoths are the ice giants of Uranus and Neptune, who at some point in this violent past are thought to have been ejected from the inner solar system through gravitational influences, and now hold dominion within its outer reaches. Multiplanetary systems like the solar system have in the vast majority of discoveries formed along these lines, where planets collide and jostle for position, or have been gravitationally perturbed by larger objects. In contrast, HD 110067 seems to have escaped the extremes of this violence during its formation. Following the initial collapse of the gas and dust cloud, a protostar formed. Over time, protoplanets emerged that then became planets with their orbits remaining untouched by significant collisions or gravitational perturbations from massive planets and passing stars ever since. The only real influences has been from their star and the gentle gravitational tug each planet gives, and in the process it has allowed the system to establish synchronous orbits known as an orbital resonance, occurring where 2 or more objects exert periodic gravitational forces on each other. Orbital resonance is a gravitational phenomena where stable and repeating orbital patterns occur. For example, the inner of 2 planets in orbital resonance may complete 2 orbits for every 1 orbit of the outer planet. Discovered in 2020 by NASA's Transiting Exoplanet Survey satellite, TESS, HD 110067 revealed its synchronicity over a 3-year period of observations through TESS, ground-based telescopes, and the European Space Agency's Characterising Exoplanet satellite. From the initial realisation there were 2 planets orbiting this star, 6 planets were subsequently discovered, all orbiting within a radial distance less than that of Mercury to our Sun. This close to their star, these 6 exoplanets are hot and gassy, with all sharing a strikingly similar size, hovering between 2 and 3 times the size of Earth. Known as sub-Neptune planets, the most common planets in the galaxy, none are gravitationally dominant within the system, and this lack of any one planet massively affecting the others has contributed to an absence of perturbations within the system. This has helped shape the system, where a rare but unique orbital pattern has evolved, with all 6 planets moving through it in an orbital resonance never before seen, especially for so many planets. Each exoplanet has orbital periods of 9, 13, 20, 30, 41 and 54 days, with the innermost planet completing 3 orbits around the star for every 2 of the next planet, creating a metronomic 3:2 orbital resonance. This 3-to-2 resonance pattern persists through the first 4 planets, with the outer 2 planets having a 4-to-3 resonance. And at 54 days orbital period for the outer planet, the inner planets at 9 days complete 6 orbits for every one the outer planet does. Planetary systems, including our own, are thought to have evolved from varying conditions, with many experiencing orbital resonance in their early formation. However, with less than 1 in 100 systems retaining this synchronicity, HD110067 is exceptionally rare, but has gifted scientists the opportunity to look billions of years into the past at a planetary system frozen in time shortly after its formation. Exploring HD110067 and its sub-Neptune planets will provide scientists with an invaluable baseline that may offer insights into the complex mechanisms governing planet formation and migration within planetary systems. It could shed light on the peculiar absence of sub-Neptune planets in our own system, as well as allow scientists to fine-tune planetary system models as we understand more about the myriad of influences that have shaped their formation. Thank you so much for watching, and if you enjoyed it, please consider giving it a thumbs up and subscribing if you haven't already done so, as your support is greatly appreciated.